For almost all of human history, if you wanted to make light, you had to make fire. I mean, from a caveman's torch all the way to an Edison bulb, light was really just a side effect of getting something incredibly hot. But then everything changed. We figured out how to skip the heat entirely and create light directly from electricity. Today, we're going to explore that incredible quantum leap that made the humble LED possible. And this slide really breaks it all down. On the one hand, you've got incandescence, the old way. It's all about brute force heat. It happens in our big, macroscopic world, and man, is it inefficient. But on the other hand, you have electroluminescence, the new way. This is all driven by electric current, happening down in the microscopic quantum world, and it is stunningly efficient. This one shift from heat to current is really the heart of the whole story. So first, let's just take a quick look at that old world order. For centuries, the rule was simple. If you want light, you've got to accept a whole lot of wasted heat along with it. The science behind it is called incandescence. All it really means is you take a material like that tiny tungsten filament in an old light bulb, and you just run electricity through it until it gets so ridiculously hot that it starts to glow. It's basically a controlled fire trapped inside a little glass bulb. And here's the fundamental problem with that. Most of the electricity you're pumping into an incandescent bulb isn't making light at all. Nope, it's just escaping as invisible infrared radiation, which we just call heat. That makes it less of a light bulb and more of a tiny, very inefficient space heater that just happens to glow. But what if you could just bypass the heat altogether? I mean, what if you could skip that step? Answering that question sparked a quantum revolution and gave us a completely new way of making light. The principle behind it is called electroluminescence. Yeah, I know, it's a mouthful, but the concept is actually beautiful in its simplicity. You have a solid material that emits light directly when you pass an electric current through it. There's no middleman, no heating required. It's just electricity in, light out. And this really shows what a massive scientific leap we're talking about. We literally left behind the clunky, brute force world of thermodynamics, boiling water and glowing hot filaments. And we entered this precise, elegant, and microscopic world that's governed by the laws of quantum mechanics. So how does it actually work? Well, to understand that, we've got to zoom way down to the atomic level and meet the two key players in this little quantum dance, the electron and the hole. The magic really starts with a process called doping. So imagine you have a perfectly pure crystal of a semiconductor. Scientists will intentionally introduce these tiny specific impurities into it. If they add an impurity that brings along extra electrons, they create what's called an N-type material, N for negative. And if they add an impurity that's missing electrons, they create a P-type material, P for positive, which is now full of these things called holes, which are really just empty spots where an electron ought to be. Okay, so now you take these two different materials and you sandwich them together. That creates something called a PN junction. When you apply a voltage, when you turn it on, it's like a starting gun goes off. The electrons from the N side are pushed towards the middle, and at the same time, the holes from the P side are pushed from their side to meet them. Right there at the junction, they finally meet, and an electron falls into one of those empty spots or holes. And right there, in that tiny moment of recombination, something truly amazing happens. See, the electron is moving from a high energy state to a lower energy one, and all that extra energy has to go somewhere. In the right kind of material, it's released in its purest possible form, as a single particle of light, a photon. And that's the light that you see coming from an LED. But there was a massive problem. For decades, scientists really struggled with this because, as it turns out, not all semiconductors are created equal. Getting that energy to actually turn into light, instead of just more heat, was the great scientific challenge of the time. And this gets to the absolute heart of the problem. It all comes down to something called the band gap. In a direct band gap material, the electron and the hole have their momentum perfectly aligned. They can recombine very simply, and that energy is released cleanly as light, a photon. But in an indirect band gap material, their momentum is all misaligned. They actually need a third party, a phonon, which is basically a vibration or heat, to get involved just so they can recombine. It's a clumsy, inefficient process that turns most of the energy into, you guessed it, heat. And this quote, wow, it really drives home just how high the stakes were. This one single distinction, direct versus indirect, was everything. It separated the materials that could one day light up our entire world from those that were just scientific dead ends, leading to decades of agonizing failures for brilliant researchers. And you have to appreciate the irony here.
With the wrong materials, these pioneering scientists had accidentally recreated the very problem they were trying so hard to solve. They'd built this amazing quantum mechanical device that was, well, just another inefficient heater, echoing the exact same flaw of the old light bulb they wanted to make obsolete.
So, the mission became crystal clear. Find and perfect the right direct bandgap materials. This final chapter is all about how scientists basically learn to paint with crystals, creating specific colors of light by cooking up brand new atomic recipes. And you can see the methodical progress right here on this chart. Scientists became material alchemists. They figured out that different atomic recipes would change the size of that all-important band gap, which in turn determines the color of the light that gets emitted. An alloy of gallium and arsenide that produced invisible infrared light. But add some phosphide to the mix, and you could tweak it to create red and orange. A different recipe with gallium phosphide gave them green. Each new alloy was a brand new color in their quantum paint box. Now, of course, these early LEDs couldn't light up a room, not even close. They were small, low-power devices, perfect for things like the little indicator lights on your stereo or the glowing red numbers on a digital alarm clock. This was a really critical pre-blue era, and it laid all the groundwork for the lighting revolution that was just around the corner.
So to really get this, you've got to rewind the clock, way back, over a century ago, to a time when the whole idea of making light come out of a solid crystal without any heat sounded like something straight out of science fiction.
Okay, so our story kicks off in the workshop of a pretty well-known British engineer, a guy who just happened to stumble upon something absolutely extraordinary, and then, well, he kind of just shrugged and moved on. And you have to appreciate the timing here. It's just incredible. Look at this, 1907. This is only 4 years after the Wright brothers first got a plane in the air. It's the same year the very first synthetic plastic was invented. The science that could even begin to explain what was happening in that crystal, I'm talking quantum mechanics, was barely even a thing yet. So you've got this guy, Captain H.J. Round. He's working for the radio pioneer Marconi, and he's fiddling with one of these old-timey radio detectors. He passes about 10 volts through a little crystal of silicon carbide, and poof, it starts to glow. He thinks, that's weird. He writes a quick 2-paragraph note about this curious phenomenon, and that's it. It's just a weird side effect to him, a laboratory curiosity. Nothing more. But of course, the story doesn't end there, not even close, because almost 20 years later, that same glowing effect was rediscovered independently by a very, very different kind of person. And this is where our real hero enters the story. And this comparison just lays it all out, doesn't it? On one side, you have Captain Round, formerly trained part of the scientific establishment. He sees something by accident and moves on. And on the other side, you have Oleg Lucev, a self-taught technician, no fancy degree, who finds the same effect and becomes completely obsessed with figuring it out. And this is so crucial to his story. Lucev was, by all accounts, a genius. But because he was born into a noble family in Russia, the Bolshevik Revolution completely shut him out of getting a university education. He had to take a job as a low-level technician. But, you can't suppress that kind of brilliance. See, this is where things get really fascinating. Because where Captain Round saw a little curiosity, Lucev saw a deep, fundamental law of physics at work. He wasn't happy just seeing the glow, he absolutely had to know why it was glowing. And his method for proving it was just so clever, especially for the 1920s. He basically thought, okay, if this light is coming from heat, like the filament in a light bulb, the crystal should get crazy hot and start to, burn off. So he meticulously measured it, and he found nothing. No major heat, no evaporation. He proved this was a totally new kind of light, a cold light. Now, at the time, the biggest thing in physics was Einstein's photoelectric effect. It was this groundbreaking idea that explained how light could create electricity. It's the whole principle behind solar panels, right? Light goes in, electricity comes out. Everybody knew that. Well, Lucev, this technician with no degree, working in a lab in the Soviet Union, he has this absolutely staggering insight. He figures out that what he's seeing is the exact inverse of Einstein's famous theory. He proposed that you could put electricity in and get light out, that an electrical current could be turned directly into particles of light. I mean, this was a quantum leap in thinking, decades ahead of everybody else. And get this, his genius didn't even stop there. It wasn't just about the light. Lucev saw the massive potential of what he started calling solid-state electronics.
He envisioned a future that didn't need these big, clunky, fragile vacuum tubes for everything. Seriously, let this sink in. He patented a light relay. He was basically predicting fiber optics, high-speed communication using light all the way back in the 1920s. And while he's working on this stuff, he discovers he can use his crystals to amplify radio signals. He creates the very first solid-state amplifiers and radios. This work predated the invention of the transistor at Bell Labs by a quarter of a century. The guy was just on another level. So, the big question, right? If this guy was so brilliant, so far ahead of the curve, why isn't Lucev a household name like Edison or Marconi? Well, the answer is just a perfect storm of bad history, bad timing, and terrible tragedy. For starters, he was publishing his work in Russian journals at a time when the Soviet Union was pretty cut off from the rest of the world. Meanwhile, everyone else was completely obsessed with vacuum tubes. They weren't interested in some weird crystal tech from a guy nobody knew. Without a degree, without a powerful champion for his work, his revolutionary ideas were just ignored. And then, the story takes its darkest turn. Oleg Lozev died of starvation in 1942 during the horrific siege of Leningrad in World War II. He was only 31 years old. His work, his vision, his notebooks, pretty much everything was lost in the absolute chaos of the war. And for decades, he was just a footnote in a few obscure journals. But his legacy, it turns out, was just waiting in the dark to be seen again. So really, the next time you look at your phone or see the headlights on a car, or even just the little power light on your computer, remember Oleg Lucev. Remember the self-taught genius who first truly understood the physics of that glowing crystal, who saw the entire future in a tiny, faint spot of cold light. His name might have been forgotten, but his legacy, it is, quite literally, everywhere you look. All right, so our story kicks off right after World War II. This was just a time of insane scientific progress. The invention of the transistor back in '47, that really laid the groundwork for all modern electronics, and this is the crucial part, for semiconductor technology. So by the mid-50s, scientists were getting kind of tired of using these unreliable, naturally occurring crystals. They shifted their focus to compounds they could engineer with incredible precision. And you know what? This new approach paid off fast. In 1955, a researcher named Reuben Brownstein over at RCA noticed something amazing. A simple diode made of this stuff called gallium arsenide could emit infrared light. Now, the secret sauce here, the reason gallium arsenide worked so well, is a property called a direct band gap. Think of it like this. If electricity is a ball, in most materials, it just kind of bounces around, losing energy before it has a chance to become light. But gallium arsenide, it gives that ball a straight shot, a direct path, which makes it incredibly efficient at turning electricity right into light. Something the silicon and our computer chips, by the way, is just terrible at. Building on this, researchers at Texas Instruments had a huge commercial breakthrough in the fall of 1961. They created this super efficient infrared emitting diode, and they immediately realized, whoa, this has massive potential for things like optical data transmission and sensors. But there was a catch. A pretty big one, actually. The light's wavelength was stuck in the near infrared part of the spectrum, which meant their revolutionary new light source was totally invisible to the human eye. So this led to the world's very first commercial LED product in 1962, the SNX 100. And it was great, perfect for stuff like remote controls and card readers. But the ultimate prize, a solid-state light that you could actually see, that remained frustratingly out of reach. And this is where our main character enters the story, Nick Holonyak Jr. He was this brilliant engineer at General Electric, and he was absolutely determined to drag this semiconductor light out of the infrared shadows and into the visible world. So Holonyak was the son of immigrants and, get this, the very first graduate student of John Bardeen, the guy who co-invented the transistor. For him, this wasn't just about building some new device. He was driven by this deep personal mission to actually see the light he was trying to create, not just, measure it with some sensor. Now, over at GE, he found himself smack in the middle of this fierce global race to build the first semiconductor laser. You had teams from IBM, MIT, RCA, everybody was in on it. In fact, his own colleague at GE actually built one first. But just like those earlier diodes, its light was totally invisible. But Holonyak, he was aiming for something completely different. And to do that, he couldn't just use some off-the-shelf crystal. No,
he had to invent a brand new one from scratch. He basically needed to write a completely new recipe for light. Okay, so Holognac's theory was both elegant and honestly kind of audacious. He started with gallium arsenide, which they already knew was an infrared emitter. Then he theorized that if he could just swap out some of the heavier arsenic atoms for lighter phosphorus atoms, he could create a whole new alloy, gallium arsenide phosphide. This little atomic switcheroo would physically change the crystal, widen its band gap, and force it to emit higher energy light, specifically visible red light.
Now, you have to understand, this was a wild idea. Many experts at the time thought it was flat out impossible. They predicted that trying to mix 3 elements like this would just give him a lumpy, useless crystal, totally unsuitable for making the delicate structures he needed. But Holognac was not deterred. He designed and built his own custom system right there in his lab to grow this new crystal, one atom at a time. And this, right here, is the climax of our story. And then came the moment of truth. On October 9th, 1962, after all this painstaking work growing his unique crystal alloy, Holognac took the new component he just forged and he applied an electrical current. And there it was. For the very first time in history, a solid-state device emitted a light that a human being could actually see, a distinct, bright red glow. I mean, the achievement was so revolutionary, it felt like actual magic. His colleagues at GE were just astounded. They didn't even have a technical name for it. They called it the Magic One. But Holognac's vision didn't just stop with that first little red glow. Oh no. He immediately understood the profound implications of what he had just created. Just a few months after his invention, he made this incredibly bold prediction in, of all places, Reader's Digest. He said that his tiny, super efficient solid-state lamps would one day replace Thomas Edison's fragile, inefficient incandescent light bulb. And you know what? He was right. The last piece of the puzzle fell into place in the 1990s with the invention of the blue LED. That was the missing primary color they needed to create white light. And with that, almost exactly 50 years after he said it would, Holognac's prophecy came true. LEDs started to replace incandescent bulbs all over the world. Okay, picture this. It's the early 1970s. Scientists all over the world are in this intense race. They've already figured out red LEDs, but that's not enough. The real prize is getting a whole palette of bright colors. Everyone was chasing orange, yellow, and especially green.
Now, the game plan seemed pretty simple. It was called the Alloy Road. And the idea was you take the basic recipe for a red LED, that's gallium arsenide, and you just start adding a new ingredient, phosphorus. The theory was the more phosphorus you mix in, the more the color shifts, going from red to orange to yellow. Seemed logical, right? But as they went further and further down this road, bam, they hit a wall, a hard wall. As soon as they added enough phosphorus to get into that yellow range, the LEDs didn't just change color. They basically just turned off. They became incredibly, catastrophically dim. It was this massive, totally unexpected problem.
So to get why this happened, we need just a tiny bit of physics. I promise it's pretty straightforward. Inside an LED material, you've got this thing called a band gap. You can think of it like an energy hurdle an electron has to jump over to create light. Now, a direct band gap, that's a nice, easy jump, super efficient. An indirect band gap, that's a clumsy, awkward jump that pretty much never works. And that was the heart of the problem. The material for red LEDs had that efficient direct band gap, but when scientists added all that phosphorus to try and make it yellow, the material itself changed its mind. Its fundamental structures shifted to that super inefficient indirect band gap. And the result? The light output just fell off a cliff.
So it really seemed like a dead end. You know, a law of physics you just can't argue with. But in 1972, a researcher named M. George Crawford figured out a way to cheat. He came up with this incredibly clever workaround. His solution was to add nitrogen into the crystal mix. Now, what the nitrogen did was create these tiny little energy pockets, or traps. They acted like little molecular anchors. And these traps could grab onto electrons as they passed by and just hold them there, basically setting them up to make that difficult jump perfectly. So here's how this ingenious trick played out. The nitrogen atoms get in there and create those little energy traps.
As electrons are moving around, these traps snag them and hold them still, just long enough for them to make that tough jump and release a photon of light. Crawford's trick essentially forced an inefficient material to act like it was an efficient one. It completely sidestepped the physics problem.
And the impact was immediate. And it was massive. This technique didn't just lead to the world's very first yellow LED. When they applied the same trick to the existing red and orange LEDs, it made them 10 times brighter, a 10x improvement. This was the breakthrough that really started to move LEDs beyond being just tiny indicator lights. But the story definitely doesn't stop there, because as the industry rolled into the 1980s, a totally new approach was about to take that 10x improvement and do it all over again. See, up until this point, all LEDs were what you'd call homojunctions. They were made from one single continuous piece of material. The new idea was called the heterostructure, and it's basically an atomic scale sandwich made of different materials, layered one on top of the other with incredible precision. And the genius of the sandwich design was that it acted like a tiny, high-tech prison. It trapped both the electrons and the light they created in a super thin layer right in the middle, forcing them to interact. This just massively increased the chances of light being emitted and cut way down on any wasted energy. And the results were just staggering. These new heterostructure devices blew away all the old records, reaching up to 10 lumens per watt. That's another 10-fold increase in efficiency. For the very first time in history, a red LED was officially more efficient than a regular old incandescent light bulb with a red filter on it. A huge milestone. Now, this science was incredible, but it came with a huge catch. How in the world do you actually build these perfect atomic-level sandwiches, not just once in a lab, but in a factory, millions and millions of times? This needed a whole new manufacturing revolution. The old way of doing things, called liquid phase epitaxy, was kind of like dipping a wafer in molten material. It was slow, it was clumsy, and it was nowhere near precise enough for these new ultra-thin layers. The solution actually came from the computer chip world, a new process called MOCVD, which is basically like spray painting crystals onto a wafer, one atomic layer at a time. The pioneer here was a researcher named Russell Dupuis, and you gotta love this detail. He didn't have some fancy multi-million-dollar lab. He proved this whole revolutionary theory was possible by building his very first reactor from spare parts in a machine shop. That's just a perfect story of pure hands-on ingenuity. And that work by Dupuis was really the last critical piece of this puzzle. MOCVD was the tech that finally let these advanced LEDs escape the lab and become affordable, mass-producible components that were truly ready to change the world. And so, after about a decade of just relentless innovation, the stage was finally set. You had this combination of clever physics, revolutionary design, and groundbreaking manufacturing, and it unlocked the true potential of the LED. Suddenly, LEDs were bright enough, efficient enough, and cheap enough to break out of small electronics. They started showing up and really demanding applications, right? Car brake lights that could turn on instantly, a fraction of a second that can literally prevent an accident, ultra-reliable traffic signals that save cities a fortune on energy and maintenance, and of course, those huge, vibrant message signs on the highway that were totally impossible with the old tech. When you look back, it was just this incredible 10-year sprint. The big takeaway here is how innovation is almost never just one aha moment. It's a chain reaction. You had a physics workaround, then a new design, then a manufacturing leap. And all together, they took LEDs from a dim little component to a world-changing technology. You see, back in the 1960s, the very first solid-state lights weren't destined for your living room lamp. Oh no, they were for spaceships, secret military projects, and the most cutting-edge science labs. This wasn't just another product, it was a piece of the future, built for the most demanding things you could possibly think of. That's right, $200. And that was the price for a single red gallium arsenide light unit in the early 1960s. At that cost, you weren't just buying a component, you were commissioning a bespoke scientific instrument, carefully crafted one by one. So what this really meant was that these little glowing dots were reserved for the absolute elite. We're talking high-budget aerospace equipment, classified military hardware, basically places where the cost didn't matter, but failure was simply not an option. Now, what's really fascinating about this whole story is how this super exclusive technology ended up in products for everyone.
And the answer? A fierce corporate battle that basically kicked innovation into overdrive. So in one corner, you had Monsanto, yeah, the chemical company, who jumped in with the Man 1. It was the world's very first commercial numeric display. Totally revolutionary, but also really complex to use. Then, in the other corner, you have Hewlett-Packard. They fired back with a much more advanced design that actually had its own control circuit built right in, which made it 1,000 times easier for engineers to design into their products. This cutthroat competition, plus some huge manufacturing breakthroughs from pioneers over at Fairchild Semiconductor, caused prices to just plummet. I mean, what started at over $50 for a single character dropped to just a few cents per diode in only a couple of years. The floodgates were officially open. And this right here? It's the perfect illustration of what happens when a powerful technology suddenly becomes affordable. It finds its way into the hands of regular people, starting with two iconic gadgets that really defined the early 1970s. That was Johnny Carson's live, on-air reaction to seeing the Pulsar, the world's first all-electronic digital watch. He was so unimpressed with the whole idea that he just casually tossed this priceless prototype right over his shoulder. Look, the watch was an absolute marvel of engineering, no doubt about it, but its LEDs were incredibly power-hungry. They just chewed through the battery so fast that the display had to stay off by default. So to even check the time, you had to do this kind of cumbersome two-handed move. It was a neat trick at first, but, consumers eventually got tired of the novelty. At the very same time this was happening, the calculator industry was in the middle of its own revolution. They were desperate to move on from these huge, fragile desktop machines to something you could actually carry around, something truly portable. Before solid state came along, this was how you displayed numbers. These things are called Nixie tubes, and they were beautiful for sure, but they were also big, delicate, and needed so much voltage that a battery-powered version was a total fantasy. So the engineers at Hewlett-Packard used some incredible ingenuity to crack these problems. They used microscopic light sources, some of them as small as a grain of salt. And then, this is the clever part, they molded tiny little magnifying lenses right into the plastic casing itself to make the digits readable. You combine that with a hyper-efficient power system and boom, you get the legendary HP35 scientific calculator. But this whole revolution, it wasn't just about cool consumer gadgets. The technology's greatest strength wasn't its shrinking size or its fallen cost, but its absolutely incredible reliability. For industries where failure just is not an option, the difference was, well, it was night and day. Solid-state diodes had a lifespan that was, in theory, almost infinite. They were shockproof, super efficient, and they ran cool. Totally unlike the fragile, hot, and power-hungry incandescent bulbs they were replacing. Just take IBM's groundbreaking System/370 mainframe. Its operator console had hundreds of little indicator lights. By swapping out all those failure-prone bulbs for solid-state diodes, IBM drastically cut down on costly maintenance downtime, and it lowered the massive heat load on the computer's cooling systems. A huge win-win. And of course, the aerospace industry eagerly jumped on this technology. The old analog dials, which pilots called steam gauges, needed constant upkeep. But solid-state indicators led to the modern, much safer glass cockpits that are just incredibly durable and reliable. And what's really crucial here is that the super precise colors of these new LEDs allowed for a universal language of safety. Red is now reserved exclusively for critical, life-threatening warnings. Yellow is for caution, and green means normal operations. It's a standard that pilots all over the world rely on to this very day. And so this incredibly reliable and efficient technology became the invisible backbone of our modern world. From the floor number in an elevator to the status lights on a massive telephone switchboard, solid-state displays were suddenly and quietly everywhere.
I mean, when these things first hit the market, the hype was just massive. The marketing language was, well, it was aggressive. We're talking words like indestructible, everlasting. They were basically selling this idea of a light that would never burn out, a total revolution in a tiny package.
But here's the thing. Behind all that marketing flash, there was a big problem. These revolutionary lights, they were failing. And not in the way you'd expect, not with a pop or a flash. It was more like a slow, silent whimper. And for the engineers behind them, the burning question was just, why? What was going on?
And this really gets us to the heart of the mystery, what I'm calling the indestructible lie. See, the way these early LEDs were failing was, well, it was weird. It was completely different from anything people were used to.
You know how an old school light bulb dies, right? There's that little pop,
the filament snaps, and boom, it's dead. That's what you call a catastrophic failure. It's instant. But these early LEDs, they were doing something else entirely. It's called parametric failure. Basically, their light output, what engineers call luminous efficacy, or just, how bright they are, it would just slowly degrade over time. It was this slow, maddening fade into uselessness. So, let's dive into that. This first major failure mode, the slow fade to black. What on earth was causing this gradual dimming? Right, so this gets to the core concept, parametric failure. It's such a key idea here. It means the device doesn't just die. It keeps on working, but it just gets a little bit worse and a little bit worse until it's basically useless. That phone battery analogy is perfect. Imagine your phone lasting one less minute every single day. That's exactly what was happening to the light output.
And then researchers found a major clue, a real breakthrough. They realized that when the internal temperature of that little diode hit 100 degrees Celsius or went above it, this whole dimming process went into overdrive. It was like a thermal tipping point. That was the magic number.
So that discovery pointed to a really surprising culprit. Because, one of the big selling points of LEDs is that they're cold light, right? They feel cool to the touch. But the irony is, they were actually dying from intense heat, just on a microscopic level.
So where's this heat even coming from? Well, you have to zoom way in, down into that tiny semiconductor. And there are really two things going on. First, the process of making light isn't 100% efficient. Some of that energy just bleeds off as heat. And second, the material itself has natural electrical resistance, kind of like friction for electrons. So you put those two things together, and you get this tiny but intense pocket of heat.
And this is where things get really bad, because it creates this destructive feedback loop, a vicious cycle. The heat increases, which makes the electrical resistance go up. But higher resistance generates, you guessed it, even more heat. And around it goes. This loop gets so bad it literally causes the atoms inside the semiconductor to start moving around. It's a process called atomic diffusion. And it just strangles the device from the inside out. And the light output? It just tanks. But get this, that wasn't even the only problem they were facing. As if that wasn't enough, while engineers were trying to solve this microscopic heat issue, a totally different and, honestly, kind of bizarre failure started popping up. I'm calling this one the case of the yellowing plastic. And here's the crazy part. You'd think, okay, the problem has got to be with that super advanced, high-tech semiconductor chip, right? The brains of the operation. But nope, it wasn't that at all.
The real culprit? It was the cheap plastic shell. That simple, clear dome that was only supposed to protect the tiny chip inside. That supposedly inert little piece of epoxy resin was literally attacking the very light it was meant to be focusing.
Okay, so here's what was happening. It's a process called photooxidation. The high-energy photons, the blue light basically, were acting like tiny little cannons, just blasting apart the polymer chains that made up the epoxy. This process created these super unstable things called free radicals. And these free radicals then grabbed onto any nearby oxygen, and they formed completely new and totally unwanted molecules right there inside the plastic.
These new, nasty little molecules are called chromophores. And here's why they're so bad for an LED. They act like tiny little sponges, but only for certain colors. They love to soak up light in the blue and green parts of the spectrum. So they were literally absorbing those colors before the light could even get out of the plastic dome.
And this wasn't just a cosmetic issue. This had serious, real-world consequences. Think about a critical green indicator light in, say, an airplane cockpit. Over time, because of these chromophores, it would slowly turn into this sickly, ambiguous yellow color. I mean, what does yellow mean? Is it on? Is it off? Is it a warning? This chemical breakdown made critical safety indicators completely useless. That's a huge deal. So, okay, the engineers are facing two completely different but very serious problems. They had to get incredibly creative. And this challenge really kicked off a new era of innovation, all focused on engineering the perfect light.
So how did they solve it? Well, to fight that microscopic heat, they threw everything at it. New advanced thermal materials, super clever heat sinks to draw the heat away, and new circuits to carefully control the electrical current. And for the yellowing plastic, the chemical engineers just gave up on the cheap stuff. They completely abandoned those old epoxies and developed amazing new resins and advanced silicones that were basically immune to that light-blasting photooxidation.
And the result of all this incredible engineering, well, they finally did it. That promised 50,000-hour lifespan, it became a reality. You could say the truly indestructible light was finally born, forged in the fire of its own early failures.
let me tell you a story about one of the most important inventions of the 20th century. And it all comes down to the creation of a single color. It's this incredible scientific quest that took decades, faced just impossible odds, and in the end, it unlocked a technology that literally illuminates our entire world. This is the story of the blue LED. I mean, think about it. We've had LEDs for over half a century. They were in our old digital clocks, our first calculators. They've been around forever. But for the longest time, they couldn't do the one thing that seems so obvious: replace the plain old light bulb. So what was the holdup? What was missing? Well, the answer is way simpler than you might think. A single, crucial color. You know, the potential for LEDs was obvious from day one, but that grand, world-changing vision was locked away behind one single, seemingly impossible scientific barrier. As early as 1963, one of the LED's inventors, Nick Holonyak Jr., he saw the future crystal clear. He had this vision of these tiny, super efficient diodes completely kicking the old Edison bulb to the curb. The only problem, the science just wasn't there yet. So instead of lighting up our homes, LEDs got stuck doing these kind of niche jobs. You know, they were the little red power light on your stereo, the green glow on your computer, the numbers on your alarm clock. They were useful, for sure, but they were not fulfilling that grand vision of lighting up the world. Right, so to replace the light bulb, you need white light. Simple enough. But creating white light with an LED, that turned out to be a massive scientific headache. And it all comes down to some pretty basic physics. See, here's the thing. White light isn't really its own color. It's just what our eyes and our brains perceive when a whole bunch of different colors, different wavelengths of light, get all mixed together. So if you want to make a white LED, you've got to figure out how to generate that whole spectrum. And scientists really had two main ways to pull this off. The first one was just to mix the light from red, green, and blue LEDs together. But the other method, which turned out to be way more efficient, was to use a single high-energy blue LED to light up a yellow phosphor coating. That combination of blue and yellow light would trick our eyes into seeing it as white. Are you seeing the common thread here? It didn't matter which path they took. Both roads led to the exact same dead end. They both required a bright, efficient, high-energy blue LED. And for decades, that was the one thing that nobody on Earth knew how to build. So why was blue so ridiculously hard? Well, its photons pack more energy than any other color we can see. To get a semiconductor to spit out that much energy, its electrons have to make a huge leap. That leap is what scientists call a band gap. And for blue light, you need a really wide band gap of about 3.4 electron volts. Finding a material that was stable and had that property, that became the holy grail of materials science. So the search basically boiled down to two main candidates. And the crazy part is, each one came with its own fatal flaw. The entire field was stuck between a rock and a hard place. On one hand, you had zinc selenide. I mean, it was beautiful. It formed nearly perfect crystals. The problem? It was fragile and would just burn out almost immediately. On the other hand, you had gallium nitride. It had the absolute perfect properties for glue light, but was a complete nightmare to work with. So difficult that most researchers just wrote it off as a lost cause. And this wasn't some small hurdle. This was a showstopper. We're talking about the biggest, brightest research labs in the world, places like RCA and Bell Labs. They poured millions into this and came up empty. Eventually, they just decided it couldn't be done and they totally abandoned the research. The blue LED was officially a dead end. But a few incredibly persistent researchers in Japan just would not give up on that so-called impossible material, gallium nitride. And they were about to spend years trying to tame this beast. So what made it so hard? Well, to make a semiconductor, you have to grow a perfect crystal layer on top of a base, which is called a substrate. For gallium nitride, the best substrate was sapphire, but their atomic structures, they just didn't line up at all. We're talking a staggering 16% mismatch. Imagine trying to build a perfectly flat wall with two totally different sizes of bricks. It's just chaos. So the gallium nitride crystals they managed to grow weren't just imperfect, they were an absolute disaster. They were, and this is a quote, riddled with billions of microscopic threading dislocations per square centimeter. It was like trying to create a flawless diamond that was almost entirely made of cracks. And these defects were way more than just ugly. Inside an LED, they acted like tiny little black holes, sucking up all the energy that was supposed to be making light. The electrons would just fall into these traps and generate nothing but useless heat. It made the material almost completely worthless for creating light. So after decades of nothing but failure, the impossible suddenly happened. In the early 1990s, two breakthroughs changed everything, almost overnight. First, researchers Isamu Akasaki and Hiroshi Amano figured out a really clever trick to grow high-quality gallium nitride crystals. And right on their heels, Shuji Nakamura found the final piece of the puzzle, a way to properly dope the material, which is a key process for controlling its electricity. And just like that, the impossible was solved. And with those breakthroughs, the barrier that had held back lighting technology for 30 long years didn't just crack, it completely shattered. The missing piece was finally found. Science had finally captured that elusive high-energy blue photon, and that single achievement set off a chain reaction that would transform modern technology forever. And the impact was immediate, and it was enormous. This one invention is the reason we have energy-efficient LED bulbs that last for years. It's the tech that creates those brilliant colors on your phone, your TV, your computer screen. It is literally the blue in Blu-ray discs. This wasn't just an improvement, it was a revolution. An achievement so fundamental that, yeah, it earned its creators the 2014 Nobel Prize in Physics. And that, right there, is the big question, isn't it? How did this one little light-emitting diode not only change physics and technology forever, but also spark a massive battle between a lone inventor and a corporate giant? It's a fight that forced an entire country to rethink how it values its brightest minds. You see, it's really two incredible stories wrapped up in one tiny piece of tech. The first big breakthrough came from a researcher named Isamu Akasaki and a student, Hiroshi Amano. Their solution was just brilliantly elegant. Before trying to grow the GaN, they first laid down this super thin buffer layer of a totally different material. This little layer acted like a shock absorber, a structural bridge that soaked up all the stress between the sapphire and the GaN. And just like that, they could finally grow a near-perfect crystal right on top. At the very same time, working at a small company called Nichia, this other researcher, Shuji Nakamura, took a completely different path. He looked at the problem and said, maybe the material isn't the problem, maybe it's the machine. He figured the intense heat was just blowing the crucial gases away before they could form the crystal. So for 18 grueling months, he redesigned and built his own reactor from scratch, adding a second jet of gas to literally pin the important stuff down. It was a brute force mechanical solution to a chemistry problem, and it worked. Okay, so now they could grow high-quality crystals. Awesome, but they immediately slammed into the second huge wall. You see, an LED needs two different types of material, an N-type and a P-type, to work. Making N-type GaN was easy, but every single attempt to make the P-type layer, the positive side, had completely failed. The material just refused to conduct electricity the right way. And this is where the story gets really good. The solution to this massive physics puzzle didn't come from some grand theory or a new calculation. Nope, it came from a pure, simple, and beautiful accident. So picture this. Akasaki and Amano are looking at yet another failed sample under a powerful electron microscope, and they see something bizarre. The tiny little spot where the electron beam was hitting the material suddenly started glowing. It was working. They had stumbled onto a way to activate the material. The only problem? Blasting every single LED with a giant electron microscope isn't exactly a practical way to manufacture things. This is where Shuji Nakamura comes back in. He's the one who figured out what was really going on under the hood. He had this brilliant insight that during the manufacturing process, stray hydrogen atoms were sneaking into the crystal, and these hydrogen atoms were grabbing onto the magnesium atoms, the very atoms that were supposed to make the material P-type, and basically putting them to sleep, making them electrically useless. So once Nakamura knew the real enemy was hydrogen, his solution was incredibly, almost comically simple. He just baked the material. By heating it up in a hydrogen-free oven, the heat was just enough to shake the hydrogen atoms loose from the magnesium. The hydrogen floated away, the magnesium woke up, and the material started working perfectly. And that was a fix you could use for mass production. And just like that, both of the impossible hurdles were cleared. They could grow the perfect crystals, and they could create the crucial P-type layer. All the pieces were finally on the board to build the device that would literally change the world. So in 1993, they put it all together. They took the high-quality crystals, combined them with the now functional P-type layers, and added another clever trick, a quantum well structure that basically trapped all the energy and forced it to be released as light with incredible efficiency. This was it, the world's first bright, efficient blue LED. And for all this work, Akasaki, Amano, and Nakamura shared the 2014 Nobel Prize in Physics.
But the story doesn't end there. Not even close. Because just as the scientific war was won, a whole new battle was just getting started. This wasn't a fight about physics. This was a fight about money, about credit, and about the very definition of what an invention is worth. Look at that number, 20,000 yen. That is what Shuji Nakamura's company, Nichia, paid him as a bonus for his patent, his world-changing invention. At the time, that was worth less than $200 for an invention that would go on to create a multi-billion-dollar global industry. $200. As you can probably guess, Nakamura eventually left the company, and then he sued them. The case became a huge international spectacle, and the media, trying to capture the sheer injustice of it all, gave him this notorious nickname, Slave Nakamura. His personal fight suddenly became a symbol for inventors' rights everywhere. Then, in 2004, the Tokyo District Court came back with a verdict that was just staggering. They ordered Nichia to pay Nakamura 20 billion yen. Let me say that again, 20 billion yen. That's about 189 million US dollars. It was by far the largest amount ever awarded to an employee inventor in the history of Japan.
Now that massive 20 billion yen figure didn't stick. It was later reduced on appeal, and the two sides reached a final settlement of 840 million yen, which is about $8.1 million. And yeah, it's a big reduction, but make no mistake, the message had been sent. This was still a landmark, game-changing victory that put corporate Japan on notice.
You know, the impact of Nakamura's lawsuit went so far beyond just his own bank account. It was a massive wake-up call. It forced Japan's very rigid corporate system to completely rethink how it treats its most creative and valuable employees. It led directly to changes in patent law and to new bonus structures across the entire tech industry.
You know, the humble white LED. It seems so simple, right? Well, the story behind it is anything but. We're about to dive into the incredible Nobel Prize-winning scientific saga behind this tiny piece of tech that changed our world.
Yeah, I'm serious. That light bulb right above your head, it's the end result of a massive scientific quest that spanned decades. We're talking about countless dead ends, some seriously clever physics, and material science breakthroughs that, honestly, changed everything. So you're probably thinking, what's the big deal? I mean, red LEDs, we've had those since the 60s, green ones too. So why on earth was making a good, efficient, white LED a challenge that stumped some of the world's top scientists for so long? That is the core mystery we're going to unravel.
All right, so to really get this, you have to know that the story doesn't start with fancy TV screens or anything like that. It starts with a huge multi-billion-dollar mission to finally kill the old incandescent light bulb. You know the ones, they were basically just tiny, super inefficient heaters that happened to glow. The invention of a bright blue LED wasn't just about adding a new color. Everyone saw it as the final piece of the puzzle, the engine that could finally create a solid-state white light and change the world.
Okay, so the first idea that everyone had was the most obvious one. It was super straightforward. Hey, we've got red, green, and blue LEDs. Let's just stick them all together in one little package. You mix the primary colors of light and bam, you should get white. It seemed like a total no-brainer, just a simple engineering problem. And look, this RGB method did have some pretty cool tricks up its sleeve. You could get dynamic, tunable color, which is awesome. But the downsides? Oh man, they were absolute deal breakers. For one, it was ridiculously expensive and complicated to make. You needed 3 separate chips, 3 separate drivers. It was a mess. Worse, the different colors faded at different rates. So that crisp white light you bought, a year later it's this weird, sickly, off-color glow. But the real nail in the coffin was the quality of the light itself. Just look at this chart. This right here shows the fatal flaw. See those 3 skinny, spiky lines? That's your red, green, and blue. The light wasn't a full, smooth spectrum like you get from the sun. It was just these 3 little peaks with these massive, gaping holes in between. And what that meant was that colors in the real world looked awful under this light, totally washed out and unnatural. For general lighting, yeah, this was a complete dead end. So with the RGB approach dead in the water, the scientists had to make a major pivot. They went for a totally different, and frankly, a much more elegant solution. It's called phosphor conversion. And this new idea went all in on that brand new, high brightness blue LED. The magic behind this is a really cool bit of physics called the Stokes shift. And the idea is actually beautiful in its simplicity. You take a material, you hit it with high energy light, like blue light, and that material absorbs the energy and then spits it back out as lower energy light, like yellow or red. It's basically a way to down-convert light from one color to another. Pretty clever, right? Okay, so here's how they pulled it off. You start with a really powerful little blue LED chip. Then, you coat that chip in a special yellow glowing powder called a phosphor. You turn on the power, and the blue chip blasts the phosphor with blue light. The phosphor soaks up some of that blue light and, using that Stokes shift we just talked about, re-emits it as a nice, broad spectrum of yellow light. But here's the trick. The coating isn't totally opaque. Some of the original blue light just punches right through it. So what comes out is a mix of that new yellow light and the leftover blue light. And when that combination hits your eye, your brain goes, hey, that's white. It's a brilliant optical illusion.
And that ingenious technique led directly to this little guy right here, the world's very first practical, commercially available white LED. This was released by Nichi Corporation way back in 1996. And it was a total game changer because it was cheap, it was simple, just one chip, one driver, and it was incredibly reliable.
But, of course, there was a catch. While it was a manufacturing miracle, the light it produced just felt wrong. It was cold and clinical. So while it was a huge commercial success, it was kind of an optical failure. This kicked off what we now call the color quality crisis.
And you can see exactly why right here in the numbers. We were all used to that warm, cozy 2700 Kelvin glow from an old incandescent bulb. It had a perfect color rendering index, or CRI, of 100, meaning colors look exactly as they should. These new LEDs, they were way up over 4000 Kelvin, super cool and bluish, with a pretty mediocre CRI in the 70s or 80s. The result was this harsh, sterile light that people just did not want in their homes. That blue plus yellow equals white trick was clever, but the light spectrum it created still had huge gaps. And the big missing pieces were in the deep reds and the cyans. And that's exactly why things look so weird under these lights. Skin tones looked pale, and a vibrant red apple would look kind of dull and brownish. Not great. So this set off another race. A massive, super competitive global research effort into advanced phosphor chemistry. The new holy grail was to find materials that could perfectly fill in those missing colors and finally create that warm, beautiful, high-quality white light the world was waiting for. And the big breakthrough came from a whole new class of materials, these complex things called nitrides and oxynitrides. Scientists figured out that by mixing nitrogen into the phosphorus crystal recipe, they could get it to efficiently convert blue light into those deep, rich reds and ambers that were missing. And the truly amazing part? These new phosphors were tough as nails. They worked perfectly even at the scorching hot temperatures inside a high-powered LED. The result was, well, spectacular. By creating this complex cocktail of different phosphors, a little bit to make yellow, a little to make green, and that crucial new one to make deep red, engineers could finally paint a complete picture. A full, continuous spectrum of light. Just look at this smooth curve. All of those nasty gaps are gone. This absolute mastery of chemistry is how we got the amazing LEDs we have today. Modern white LEDs can now hit a CRI of over 90, sometimes even 95 or higher. They produce this rich, warm light that makes colors pop so accurately that it's almost impossible to tell the difference from natural sunlight. This is what finally let LEDs take over the world. But you know what? The story's still not over. Because even though the color quality problem is pretty much solved, the relentless quest for perfect efficiency has uncovered another really deep and stubborn problem in semiconductor physics. It's known as the green gap. So here's the deal. The semiconductor materials we use that are super efficient at making blue light, they're great. The materials for making red light, also great. But if you try to tweak those same materials to make green light, their efficiency just falls off a cliff. It's a total disaster. And that's a huge problem, because green is the one color our eyes are the most sensitive to. Okay, so one of the main reasons for this is a really weird quantum physics phenomenon called the quantum confined Stark effect. To put it simply, when you try to force the material to make green light, you accidentally create these intense electric fields inside the chip. These fields literally pull the positive and negative charges apart. If they can't get together, they can't combine to make a photon of light. It's like trying to get two magnets to snap together while something is actively pulling them apart.
the whole process just grinds to a halt. And it's not just that one thing, it's a whole pileup of problems. You've got extreme physical strain at the atomic level, you've got that Stark effect we just mentioned, you've got tiny defects in the crystal that just waste energy as heat, and on top of all that, you have this other thing called efficiency droop, where the light output just hits a wall at high power. It is, without a doubt, one of the toughest nuts to crack in material science right now. Think about it like this. For every single dollar you spent on electricity for one of those old bulbs, 95 cents was just thrown away. It just radiated out into the room as useless heat. Now, try to imagine that scaled up across billions, literally billions of light fixtures all over the planet. That's when you start to really grasp the unbelievable scale of the energy waste we were all just living with. And that incredible efficiency created this powerful domino effect. We're not just talking about using 75 to 90% less energy, we're talking about a lifespan of over 25,000 hours. I mean, that's years of continuous use. Plus, they don't have any of that toxic mercury you'd find in the curly CFL bulbs. And because they're solid state, you can drop one and it probably won't even break. It was a technology with, well, pretty much no downsides. So you can imagine, when a technology this good comes along, one that promises to slash a huge chunk of the world's electricity use, governments tend to pay attention. The massive potential for energy savings with LEDs, it was so obvious that it kicked off this wave of new laws all around the world, all designed to get rid of those old, inefficient lights for good. And you can literally watch the dominoes fall right here on this timeline. Australia was an early mover back in 2007. The EU followed starting in 2009. Now, India did something really interesting in 2014. They didn't just ban the old bulbs. They proactively gave out over 270 million affordable LEDs directly to people. And then finally, after years of back and forth, the US put the final nail in the coffin for incandescence in 2023. That one move is estimated to save American consumers almost $3 billion a year. Now, this massive global shift created, and I'm not exaggerating, an existential crisis for the big lighting companies. For 100 years, their business model was incredibly simple. Sell people glass bulbs that you knew were guaranteed to burn out. So what do you do when your brand new product lasts for a decade, maybe even longer? Yeah, you have to completely reinvent your entire business. Philips is the perfect case study for this. As early as 2006, they saw the writing on the wall and just pivoted hard into LEDs. They knew their old business model was totally dead. So eventually, they spun off their entire lighting division and rebranded it as Signify, a name that reflects a totally new way of thinking, where light isn't just for seeing, but for connecting and communicating. So how do you sell something that almost never needs to be replaced? Well, you stop selling the thing, you start selling the light itself. This led to this brilliant idea called light as a service. So instead of buying thousands of bulbs, a big company or a city pays a subscription for guaranteed perfect light. Signify, the provider, owns and maintains all the gear. This totally flips their incentive structure. Now they're financially motivated to make the most durable, most efficient, longest-lasting product they possibly can. It's genius. And this big shift, from selling hardware to selling a service, it sets the stage for something even bigger. The most visible impact of this whole LED revolution is happening right above our heads, on our city streets. See, street lighting has always been one of the biggest bills for any city, and LEDs were about to change that forever. This city of Los Angeles was a huge early proving ground. Starting way back in 2009, they took on this massive project to replace 140,000 of those old orange glowing sodium streetlights. And the result? Just look at that number. A staggering drop in energy use for street lighting by over 60%. And that energy saving, it translates directly into cold, hard cash. For the city of LA, this one project saves taxpayers about $10 million every single year. That's money that can go right back into other city services, all because of a more efficient light bulb. The environmental impact is just as incredible. All that saved energy is the same as eliminating over 40,000 tons of CO2 emissions year after year. And remember, this is just from one city, making one technological switch. Imagine this scaled up globally. But here's where it really gets futuristic. See, because LEDs are electronic, you can hook them up to sensors and tiny computers. So now, they can monitor traffic flow and even check air quality. They can dim themselves down when no one's around to save even more power. They're gathering data to help plan cities better. They're basically becoming the nervous system for the Internet of Things. These aren't just streetlights anymore. They're the true foundation of the smart city. And the revolution didn't stop with streetlights. Not even close.
The special properties of these solid-state lights have caused this ripple effect into some of the most unexpected places, completely changing how we think about our cars, our health, how we grow our food, and even how we send data.
Take cars, for example. It actually started with brake lights back in the 90s, because LEDs turn on instantly, giving the driver behind you a crucial extra split second to react. By 2006, Lexus rolled out the first all-LED headlights, and today their tiny size is what allows for all those super sleek, futuristic car designs. And the new advanced matrix headlights, they can literally carve a dark tunnel around other cars so you can keep your high beams on without blinding anyone.
Now, let's go inside our buildings. LEDs have opened up this whole new field called human-centric lighting. It turns out we have these special receptors in our eyes that don't help us see, but they do help regulate our internal body clock. HCL uses LEDs to perfectly mimic natural sunlight during the day, which supports those natural rhythms and has a huge impact on our health and how productive we are.
It's pretty simple, really. During the day, you want blue-rich light, kind of like the midday sun. It suppresses the sleep hormone, melatonin, and that makes us alert and focused. Perfect for an office, right? But if you get blasted with that same blue light at night from your phone or your regular light bulbs, it tricks your brain into thinking it's still daytime, messing up your sleep. HCL systems are smart. They dynamically change the color of the light to match the time of day, giving us the right kind of light at exactly the right time.
The ability to precisely control the color of light has also totally changed farming. In these huge indoor vertical farms, growers can create custom light recipes. They use very specific wavelengths of red and blue light to essentially tell plants exactly how to grow, to maximize their size, their nutritional value, even their flavor, all while using way less energy than old-school greenhouse lamps.
And maybe the most mind-bending application of all is something called Li-Fi, or light fidelity. You see, LEDs can be flickered on and off millions of times a second, way too fast for our eyes to even notice. And they can use that flickering to transmit data. This means that every single LED light in a room could become an ultra-fast, ultra-secure wireless router, using light waves instead of radio waves.
All right, let's talk about the great screen war. No, seriously, there is a fierce technological battle happening right behind the screens we look at every single day. It's this incredible story of light and chemistry and some mind-bending engineering. And it all kicked off with one really simple, really annoying problem. You know exactly what I'm talking about, right? You're watching a movie on an older TV, the scene goes dark for suspense, but the screen doesn't. It's just kind of glowing this weird muddy gray. So why? Why couldn't we get true, inky, perfect black? Well, it turns out that one simple question is what kicked off an absolute revolution in display technology.
See, for decades, the main tech out there was the LCD, and it had a fundamental flaw in its design, and it all boils down to how it tried and honestly kind of failed to create darkness.
Okay, so the best way to think about it is this. An old LCD screen is kind of like a window with a huge, bright light shining behind it all the time. And in front of that light, you've got these little liquid crystals that act like blinds, twisting and turning to try and block it. But here's the catch. They're just not perfect. Some of that light always leaks through. That's your gray. Now compare that to an emissive display. Here, every single pixel is its own microscopic light bulb. So how do you make perfect black? You don't try to block anything. You just turn the light bulb off. It's simple, it's elegant, and it's perfect.
And the first technology to really truly crack this code was OLED. That stands for Organic Light Emitting Diode. And believe me, it was a total game changer, built out of these complex carbon-based molecules that could do something that felt like straight-up magic. So what's the magic trick called? It's called electroluminescence. And here's the simple version. Engineers figured out how to sandwich these incredibly thin films of organic stuff between two electrical layers. You shoot a little current through there, the molecules get all excited, and poof, they spit out a photon of light. You're literally creating light from electricity, one pixel at a time. And the results? Oh, they were absolutely stunning. Since every pixel is its own light source, you get those perfect, deep, inky blacks we were talking about. This gives you what's called an infinite contrast ratio, which just means colors pop in a way you've never seen before. Plus, by ditching that big, clunky backlight, the screens themselves could become ridiculously thin and even flexible. This is how we got curved TVs and then those crazy rollable screens, and yeah, the foldable phones in our pockets today. But, and there's always a but, isn't there? For all of its amazing wins, OLED had a tragic flaw, a fatal weakness that was literally baked right into its name. The O for organic. You see,
Unlike the tough-as-nails inorganic crystals in a regular LED, these carbon-based organic molecules are, well, they're fragile. They literally rot over time. Heat, oxygen, moisture, all the stuff of life, actually speeds up their death. And it turned out the compounds needed to make that high-energy blue light were the weakest of all, decaying way faster than the red and green ones. This process of decay leads to the single most infamous problem in the OLED universe: burn-in. I'm sure you've heard of it. If you leave a static image on the screen for too long, think about a news channel's logo or the status bar on your phone, you are literally wearing out those specific pixels faster than all the ones around them. They permanently lose their glow, leaving this ghostly afterimage just seared into the display forever. So to try and fight this sort of civil war broke out inside the world of OLED engineering. You had two big camps. On one side, you have white OLED, or WOLED. Their strategy was to create a really stable, powerful white light and then use color filters to get red, green, and blue, kind of like a high-tech stained glass window. It was way more durable, but those filters block a lot of light, so it wasn't super efficient. Then, on the other side, you have QD OLED. Their plan was to use only the most stable blue organic layer and have that blue light hit a layer of these amazing things called quantum dots, which would then convert the light into super pure red and green. This way is way more efficient and vibrant, but it had its own issues, like struggling with reflections in a bright room. And all this innovation, this internal battle, led us to what is pretty much the peak of organic display tech: tandem OLED. This is the absolute latest breakthrough. Engineers literally figured out how to stack two complete OLED layers right on top of each other. Now, this lets them do one of two things. They can either double the screen's peak brightness, or, and this is the really clever part, they can get normal brightness while running the panel at half the power. And by doing that, they drastically cut down on the heat and the stress, which extends the lifespan by up to 4 times. This is the tech that finally made OLED tough enough to put in laptops and car dashboards without worrying so much about burn-in. But here's the thing. Even while engineers were pushing organic chemistry to its absolute limits, the entire industry was already looking over the horizon, searching for the true successor. A technology that promised to do everything OLED could do, but with absolutely none of its fatal flaws. And its name is micro-LED. Honestly, the best way to get your head around micro-LED is to picture one of those gigantic, blindingly bright billboards in Times Square, or a jumbotron at a stadium. Now, imagine taking that exact same technology and shrinking it down to an almost impossibly microscopic scale. With micro-LED, every single one of those red, green, and blue lights is its own tiny traditional LED, often smaller than the width of a human hair. And when you put them head to head, the difference is just night and day. Because micro-LEDs are made from those super robust, inorganic gallium nitride crystals, they just don't decay, they don't rot. Their lifespan is basically infinite, so zero risk of burn-in, and they can get orders of magnitude brighter than the best OLED. On paper, it is the perfect display. But there's one enormous, gigantic catch actually building one. Yeah, because trying to manufacture a micro-LED screen has turned out to be one of the single biggest engineering nightmares of our time. We're talking about a problem of almost unimaginable scale and complexity. Just look at that number, 24,883,200. That is how many individual microscopic LED chips you have to create, test, pick up, and then perfectly place just to build one 4K TV. And get this, if you mess up just a handful, literally just a few, the entire display is ruined. This whole nightmare has a name in the industry. They call it the mass transfer problem. And the challenge isn't just moving millions of tiny things, it's doing it at lightning speed with absurd precision. Think about it, a 99.9% success rate sounds amazing in almost any other field, right? Well, here, it would mean you'd have nearly 25,000 dead pixels on a single TV. It would be completely unsellable. No, to make this work, you need a success rate of 99.99999% or better. It's insane. So how on earth are engineers even trying to solve this? Well, with methods that sound like they're pulled straight out of science fiction. Okay, check this out. One of the leading techniques involves a super high-powered ultraviolet laser. They aim it through the back of the wafer that the LEDs are grown on. The laser zaps a tiny sacrificial layer right under a single micro-LED, vaporizing it instantly. This creates a microscopic shockwave that literally blasts the chip off the wafer and slaps it onto the display panel with pinpoint accuracy. They're doing this millions of times a minute. Okay, so why? Why are the biggest tech companies in the world pouring billions and billions of dollars into solving this absolute physics nightmare? It's because the company that finally cracks mass transfer doesn't just win the market for TVs and phones. No, they unlock the key to the entire next generation of computing.
And that killer application, the holy grail, is augmented reality. You see, the fundamental problem with every pair of AR glasses that exists today is that the optics, the little lenses and prisms that get the image to your eye, are shockingly inefficient. More than 90% of the light that the little display creates is just lost before it ever reaches your eyeball. So an OLED screen, it's just not even close to being bright enough. You'd never be able to see the image if you were standing outside on a sunny day.
This is where micro LED becomes the hero of the story. Its insane brightness can just power right through that 90+% light loss. It's so bright you can create digital holograms that look perfectly solid even in direct sunlight. And on top of that, it's way more power efficient, which means you need smaller batteries and you create less heat right next to your head. This is the technology that will finally let companies build true AR glasses that look and feel just like a normal pair of prescription glasses. So think about this journey. We went from those dull, gray, glowing screens to paper-thin displays that can literally roll up. And now we are right on the verge of a technology that can seamlessly, believably merge our digital world with our physical one. The perfect display, it's not a question of if anymore, it's just a question of when. And so the real question we have to ask ourselves is, what new realities are we going to build with it when it finally gets here?